Okay, in this video, we're going to continue from acids and bases, and we're going to talk about the dissociation constant. So, when you have water plus water, and I know this is not balanced, but so anyways, you would have, right, actually it is, never mind. Anyways, so alright, so when you have water, it is constantly in this equilibrium of hydronium and hydroxide ions. And they're so small that it's not really making a difference. But if you ever take the pH of tap water versus distilled water, you're going to notice a slight difference because it doesn't have the ions in it that the tap water does. So what we're going to be talking about today, and let me label these. So we have acid, base. Water is weird in that it can actually act as an acid and a base. So, the auto-ionization of water is very important to understand because it helps you calculate how much hydroxide or how much hydronium that you have in solution, which is going to be crucial for solving problems dealing with acids and bases. Because without understanding this, it makes it a little harder because you don't have this constant to fall back on. So when two molecules of water combine, when two water molecules combine, they create one hydroxide and one hydronium ion. Through the transfer of a proton. Okay, so the auto-ionization of water has a Kw constant, or it's called Kw, but it's the equilibrium constant of water. So this is a number, self-ionization, wow, can't write today. Constant of water. So we have H3O plus times OH negative, and then this is going to equal 1.0 times 10 to the negative 14. So this would be your constant right here. So multiplying, if you have one of them, you technically have both because this number doesn't change. This is your constant. So let's write that over here. 1.0 times 10 to the negative 14. Hang on 1 second. Okay, alright. So let's write some definitions right now. So your concentration of hydronium is the acidity of a solution. This is what this is equal to. And your concentration of hydroxide is the basicity of a solution, or how basic it is. Just making sure I write this correctly because I'm not the best at spelling. Basicity of a solution. Alright, so let's do some examples, because this is really not that long of a lesson, simply because there's not much to talk about. But I'm going to show you a bunch of examples that we're going to use to calculate the amount of ions, and this is where this becomes important. So, we're going to be using nitric acid, and we're going to calculate based on the concentration to find out how many hydroxide ions we have. So let's write this down. What is the hydroxide concentration in a 0.450 molar solution of nitric acid? And then that would be HNO3. It's a super strong acid if you look at that list I gave you. Alright, so how this works is, if you have the concentration for an acid, you just pop that right in the H3O box. So we have 0.450 M, and you don't really have to write M, it's kind of redundant. And then that's times OH equals 1.0 times 10 to the negative 14. So we can use this to find out how many hydroxide ions we have in solution. So I'm going to open the calculator real quick because we're going to need that. So to solve this, we divide by 0.450. That cancels, and divide by 0.450. And then this is going to give us our hydroxide concentration. It's super simple. I know a lot of you are probably happy after all the gas law and colligative property stuff, but trust me, this does get harder. This is just the bare basic stuff. So our hydroxide concentration is 2.2 times 10 to the negative 14. And then that would be your answer right here. So we're going to do another one, and then I'm going to just start making stuff up because I have two written down. So let's go to the next page. So determine the hydronium concentration. In a 1.0 times 10 to the negative 2 molar solution of sodium hydroxide. And that was horribly written, so we're going to redo that. So this is our concentration. So 1.0 times 10 to the negative 2 is equal to 1, 2, so you'd have 0.01. Yeah, molar. So this would be H3O plus times 0.01 equals 1.0 times 10 to the negative 14. So simply just divide this out. It's like you're solving for x in algebra. Alright, so we would do 1.0. Remember to use the EE button, because if you guys start plugging in times 10 to the negative 14, you're going to make errors. Divided by 0.01. So your answer is going to be 1 H3O plus 1.0, wow, 1.0 times 10 to the negative 2, or 12, not 2. And that would be your concentration. So You can also just use the exponential rule if you're comfortable with that. I'm going to show you how to do that real quick. So instead of going through this and using the calculator, if you have something simple like 1.0 times 10 to the negative 2, you could have 1.0 times 10 to the negative 14 is equal to H3O times 1.0 times 10 to the negative 2. And then you divide out 1.0 times 10 to the negative 2. And then over here, it's going to be 1.0 times 10 to the negative 2. When you have division, your exponents are subtracting each other. So that would be equal to negative 12. So your answer would literally be the same thing. So let's draw an arrow. Just be aware of that. I know it's something you guys learn in algebra, so let's do some more. Because I think I have more time. Yeah, a few more minutes. Just give me 1 second. So calculate, and this is one, these two I'm going to give you about a minute in between. Because I want you to do them, so I'm going to tell you to pause it, do it, and then unpause it, and then we'll go over it. So calculate the concentration of HCl, or actually no, we'll do OH negative, in 3 molar HCl. So pause the video and try and solve this real quick using the same steps I just showed you. So let's write this out. So over here, we're just going to write a 3 because that's what its, concentration is. So as you can imagine, this is going to be a super small number. So our concentration of hydroxide is 3.33 times 10 to the negative 15, which is even smaller than the auto-ionization constant. It makes sense because this is a super concentrated solution of hydrochloric acid. So let's do some more. Calculate the concentration of, we'll do H3O plus if, oh my god, pen's freaking out. Let's do 0.72 molar potassium hydroxide. So pause the video and take a second to work on this. Okay, so I'm going to start out. Remember, this isn't calculating pH or anything. This is just telling you, based on the auto-ionization, how much hydroxide you have in the solution, or how much hydronium you have in the solution. It tells you both because it's a ratio. So this equals 0.72 times OH. Oh wait, what am I doing? H3O, sorry. So you divide out 0.72. So 1.0 second 14 divided by 0.72. So our answer for the concentration of hydronium is going to be 1.39. (1.39) times 10 to the negative 14. So pretty much that's it for this lesson. I'm going to give you a few that I want you to practice. And then we're going to have probably a little bit of a longer video next time. That's why this one's a little short, because there's only so many that you can, so much you can say about this. So let's do, I'm going to give you like one or two more. Calculate the hydroxide concentration in a 0.0045 molar solution of, I don't even know. We'll do acetic acid. Actually, let's do something else. I don't want to do that. I'll do hydrobromic acid. So 1.0 times 10 to the negative 14 is equal to 0.0045. Let me fix this. Times OH negative. So once again, we divide out this, so we're left with OH on this side. And then our answer for hydroxide concentration is going to be 1.0 second negative 14 divided by 0.0045. So our answer, surprisingly, because I think I already did this, is 2.2 times 10 to the negative 12 m. And then that's pretty much it for how to calculate these. If you have any questions, come to office hours. These are super simple. This is probably the easiest thing you'll do in acids and bases besides defining them. And then we're going to go on to neutralization reactions, where you're going to have to use stoichiometry to calculate just, certain things about acids and bases. And we're going to go over the pH scale and how to calculate the pH of a solution. And then that's pretty much it.